Today, we're going to dig into the surprisingly deep history of chemical knowledge in ancient India. It's a story that starts with something as simple as clay and fire, but believe me, it ends with a theory of the atom that was literally thousands of years ahead of its time.
So what do you picture when you hear the word chemistry? Probably modern labs with beakers and complex equipment, right? But what did it look like, say, 4,000 years ago? Well, you might just imagine some basic crafts, but the reality was so much more complex. It was a world of applied material science, really, all driven by necessity and just incredible ingenuity. Let's start at the very beginning. All right, our story begins way back in the Pre-Harappan period. We're talking about the earliest settlements in what is now Baluchistan and Sindh. And these weren't just farming communities, these were the places where the very foundations of chemistry in India were being laid, brick by brick, or, well, pot by pot.
One of the first major clues we have about their technology is their pottery. The earliest style is what we call the buff-ware culture, and it's defined by this distinct buff, kind of light yellowish-brown color. That was their canvas, which they then decorated with these cool purplish-brown or black designs.
And right alongside that, you have the redware culture. In this case, the pottery has this really vibrant red body, which they use for some pretty stylish red and black paintings. Now, having two distinct styles like this shows they had deliberate control over their materials and their firing techniques to get exactly the result they wanted.
But here's the thing, this wasn't just art. This was chemistry. They weren't just scooping up any old clay, they were actively changing its properties. They mixed in things like mica and sand to make it stronger. And crucially, they added lime. Why? Because they figured out it stopped the pots from cracking while they dried. These weren't just artisans, they were early material scientists.
At the same time, they were getting into metallurgy. They figured out how to smelt copper from ore in these kilns and then hammer and cut it into basic shapes. But they hit a wall, a temperature wall. Their kilns could only get up to about 800 degrees Celsius. Now, that's hot, but it's not hot enough to actually melt copper so you can pour it into a mold. For that, you need around 1100 degrees. This limitation is a really key point because it was about to be completely shattered.
And that brings us to the era of the Indus Valley Civilization. This was a massive leap forward, not just for society, but for technology. This is where practical chemistry really started to forge a civilization.
Remember that temperature barrier we just talked about? Well, the Indus Valley metalworkers, they absolutely smashed through it. They reached the 1100 degrees they needed for casting. They went way beyond simple hammering into complex casting and forging. And most importantly, they weren't just using copper anymore. They were creating advanced alloys by deliberately adding tin and arsenic to make bronze.
And if you think this was just some lucky accident, think again. When we analyze their bronze artifacts, we find tin content as high as 13.21%. That specific ratio isn't random. It was intentionally engineered. They knew that adding a very precise amount of tin would create a much harder, more durable metal, perfect for sharp tools and weapons. This is sophisticated chemical engineering, plain and simple.
Their mastery wasn't just about metals either. It was also about color. That vibrant red on their pottery, that came from ferric oxide, which they created during the firing process. Those bold black designs were made with manganese dioxide. They even created these beautiful blue and green glazes from copper oxide and figured out how to dye cotton red using extracts from the madder root. Every color was its own specific chemical achievement.
Following the Indus Valley, we move into what's known as the Vedic Period. And here, chemical knowledge wasn't just for specialized industries. It became woven into the very fabric of daily life, in rituals, medicine, and new technologies.
You can really see how their knowledge of metals just exploded. Later Vedic texts, like the Atharva Veda, named 6 distinct metals, and they even had Sanskrit names and color descriptions for gold, silver, and copper. And right there on the list is the real game changer, Shamya. That's iron. The Iron Age had officially arrived in India.
And these chemical processes were a part of everyday life. The Rig Veda, one of the earliest texts, is full of references to fermentation. It talks about soma, a ritual drink made from fermented plant juice, and sura, which was basically a beer brewed from barley. At the same time, the art of dyeing wool with natural vegetable colors was flourishing, creating a world filled with red, purple, and brown clothes.
And this is where we see a really fascinating shift. Chemistry starts to merge with medicine, or Ayurveda. Certain metals took on these new medicinal properties. Gold was believed to help you live a long life, while lead was used in charms to protect against bad magic.
This is really the beginning of what you might call alchemy, or rasayana, the ancient science of trying to preserve and transform things.
And that brings us to the most profound pivot in our whole story. So far, we've been talking about what people made with matter. Now we're going to shift to how they thought about matter itself. This is the journey from practice to pure theory.
I mean, think about it. They'd mastered pottery, bronze, iron, dyes, fermentation. They could literally transform the world around them. And then, at some point, they started asking a much deeper question. What is all this stuff we're transforming? What is matter, really, at its most fundamental level?
This led to one of the world's first atomic theories, coming from a philosopher named Kanada. He proposed that all matter is made up of something he called anu. And these weren't just tiny bits of stuff. He saw them as the ultimate particles, indivisible, indestructible, and eternal. It's a foundational concept that's remarkably similar to what Greek philosophers like Democritus were also thinking about around the same time.
So Kanada classified these ultimate particles, these anu, into 4 different types. And each one corresponded to one of the classical elements. You had earth atoms, water atoms, fire atoms, and air atoms. In his view, everything you see in the world was just some combination of these 4 fundamental types. But this was only the beginning.
Now, we get to the final and, honestly, the most surprisingly modern theory of them all. This comes to us from around 400 AD, from Jaina philosophers. And their atomic theory wasn't just about what atoms are, it was about how they interact.
In the Jaina system, they called matter pudgala, and they said it exists in 2 forms: the individual atom, which they also called anu, and the aggregate, or group of atoms, called a skanda, which is kind of like our idea of a molecule. The key idea here was that all substances, everything, is ultimately made of the same kind of primordial atoms which just combine in different ways.
But how do they combine? This is where it gets incredible. The Jaina philosophers laid out a specific set of rules for chemical bonding. They said that atoms can only link up if they have opposite characteristics, like one being rough and the other smooth. One had to be, in effect, positive and the other negative. And they argued that 2 particles with the same charge wouldn't unite. They'd repel each other. The only exception was if 2 similar particles had different strengths or magnitudes of that quality. Essentially, their entire theory of how chemicals combine was based on polarity. It functioned just like magnets meeting. Particles with opposite qualities attract and link together, while particles with the same qualities push each other away.
And here's the most astonishing part of this whole thing. This sophisticated theory of chemical bonding, based on polarity, was being discussed in India around 400 AD. A similar theory wouldn't be formally proposed in Western science until the work of a chemist named Jöns Jacob Berzelius, nearly 1,800 years later.
From adding lime to pottery, to engineering bronze alloys, and all the way to a theory of atomic bonding, the history of chemistry in ancient India is just a remarkable journey. And it leaves us with a really fascinating question. If a concept this advanced existed so long ago, what other scientific knowledge might still be waiting in history, just ready to be rediscovered?